So now we want to look at how do we find the area between curves. Okay, so up to this point, we've only looked at how to find the area underneath the curve or underneath the function. So for example, if we have some function f and we're going from a to b, right, then we know how to find the area underneath of f, of course. But what if we have a second function here, say g, and now we want specifically to know the area between those two functions. So just this blue part here. Okay. So the idea of how to find them, I think is pretty intuitive. It kind of goes back to all the way back when you're formulating the distance formula and you're kind of looking at how you find the lengths, right? And what you do is you find, you take the large length and you subtract off the smaller length, and that gives you the in-between length. Same idea here, right? We can find the area underneath f, and then we can subtract off the area underneath g, and that'll leave us with just the area between the two functions. So, to state this formally, we would say that if f and g are continuous, okay, because this idea is only really going to work if they're continuous, and f of x is greater than or equal to g of x on AB. Okay, and there's ways to generalize it if they switch back and forth. Then the area between f and g is given by exactly what we just said. Okay, so we take the area underneath f, so the integral from a to b of, let's say, f of x dx, and then we subtract off the area underneath g between a and b. And we can combine this into one integral just to make it a little more compact here. Okay, so we get this. So we take the integral from a to b of f of x minus g of x dx. Okay, so this will give us the area that's just between the two curves. Now we have to keep the conditions in mind, of course, namely the fact that f of x is greater than or equal to g of x. So this is only the case when one function is always above the other function, right? They're not switching back and forth at all. But if they are switching back and forth, then we can just kind of break the integral up into pieces, putting whichever one is the larger one first on this subtraction. And we can take care of that just with the absolute value function, right? So, but first let's just do an example here. So let's say that we have the function x plus 4. Okay, so this is the function x plus 4. So this one, it's going to have y-intercept 4 and then slope 1. So it'll look something like this. Okay. And then we also have the function 3 minus x over 2. Okay, so let me write them over here. F of x equals x plus 4. G of x equals 3 minus x over 2. And we want to look at this on 1 to 4. Okay, so that's why I drew 4 tick marks down here. So g of x, then we're going to have y-intercept 3 and then slope negative 1/2. Okay, so it looks something like this. Okay, but then we're also bounding it by 1 and 4, right? So we can kind of like imagine imaginary lines here that kind of rope off this region here. So ultimately, this is the region that we want to find the area of. Okay. So all we need to do then is we just need to integrate the difference of these two functions between 1 and 4. So simple enough using the integration techniques that we have so far. Really no tricks to it or anything. So x plus 4 minus 3 minus x over 2 dx from 1 to 4. Okay. So this is going to be, we'll just simplify the inside here. So x plus x over 2, which will be 3 halves x. 4 minus 3 is plus 1. Okay. So integrating this, we get, this is going to be 3/4 x squared plus x. And then we're evaluating from x equals 1 to x equals 4. So we get, what's that, 1648 over 4 plus 4 minus 3/4 minus 1. So this is going to be 51/4 plus, or I'm sorry, it's going to be 45/4 plus 3, right, which is 12/4, so that's going to be 57/4 altogether there. So 57/4 units squared, you could say, if you want to put some units on it. Okay, so anyway, so that's the way we would find the area between these two functions here. Okay, so like I said, it's fairly straightforward. Like there's really no tricks to it here. The only kind of tricky part comes into play now when one function is not strictly larger than the other function. Okay, so we'll look at that case next. So let's just approach it with an example. So I said we can take care of it with the absolute value, but before we like write out the formula for it, let's just try to reason through it graphically here. So let's specifically look at f of x equals x squared and g of x equals 2 minus x. Okay, and we want to do this on 0 to 2. Okay. So if we start by drawing it, especially when we start to get into these in-between regions, I think it's really helpful to kind of start with like a quick picture of the graph. It doesn't need to be anything fancy, just kind of to get an idea of what exactly is going on. Okay, so this point is at 2, 4 for x squared here. And then for 2 minus x, sorry, ignore that point. This is the point. And then it's going to go down right here. I can make that a little better because that should be going through 2. All right, I think 2 actually could probably be moved over a bit. Okay. So this little triangle on the inside here, this is what we're focusing on. So the reason it's not quite as straightforward as the last one here is because if you notice here that on 0 to 1, 2 minus x is larger than x squared, right? So let's say on 0, 1, g of x is greater than f of x. Okay, we could say greater than or equal to, I guess. And then on 1, 2, they switch, right? X squared now is the larger one. So on that part, f of x is greater than or equal to g of x. So this is exactly how we want to take care of it. We want to break this up into two integrals, one with doing g of x minus f of x, and the other one doing f of x minus g of x. Okay. So we'll do the integral from 0 to 1 of g of x minus f of x. So 2 minus x squared. dx. And then we'll add on that second integral. So being able to break up the integrals like this is very useful. So this is going to be x squared minus 2, and then that'll be a plus x dx. Okay. So we'll go ahead and do this. So this is 2x minus x squared over 2 minus x cubed over 3 from x equals 0 to 1. And then this one is x cubed over 3 minus 2x plus x squared over 2 from x equals 1 to x equals 2. Okay. So just plugging everything in. So 2 minus 1/2 minus 1/3. Everything else is going to be 0. And then on this one, we have 8/3 minus 4 plus, it's going to be 2, minus 1/3 plus 2, negatives cancel, minus 1/2. Okay. So you can go ahead and combine. I can see some terms canceling here, the 2's and that 4. Yeah, I think that might be it. So we'll go ahead and combine here. So we have a 2, we have 1/2 minus 1/2, so that's minus 1. 1/3 minus 1/3, and then this 8/3, that'll be 2/3. So we have 6/3, which is plus 2. So ultimately, it looks like we're looking at 3. Okay, and I'm just realizing that when I drew this picture here, I said that the wrong part is what we're taking the area of. So maybe you caught that. We're not finding the area of that triangle. We're finding the area between the functions, right? The part between the functions would be, sorry, I don't know why it's moving, would be this part and then this part, right? So not that triangle, right? We're going between functions. So we can find the area of that triangle. That would be actually a lot simpler. We would just be, I'll do it in purple here. We would just do the integral from 0 to 1 of x squared plus the integral from 1 to 2 of 2 minus x, right? That would be the triangle right here. But this right here, this is finding it between the functions, okay? So, yeah, so let's go ahead and write down the formula with the absolute value then, which I alluded to before. So all we need here now, we don't need that one is larger than the other. We just say if f of x and g of x are continuous on a to b, okay, then the area between them is given by the integral from a to b of the absolute value of f of x minus g of x dx. Okay. So you can do it completely just algebraically using the absolute value. But I do think that in general, it's probably a little bit easier to kind of reason it out using the picture. But, you know, it's not always easy to graph these or to get a precise picture of exactly where these regions are. So we might need to default to the absolute value in that case. Okay. So let's do one just using the absolute value. So not relying on any kind of picture here. Okay. So let's look at the area between f of x equals the square root of x and g of x equals 3/2 minus x over 2. Okay. On 0 to 3. Okay. So you can draw this picture here. Again, we're looking at the part between the curves, not the part which is bounded by the x-axis, but specifically the part between the curves here. So if we were to look at the absolute value here, so if we just write it out with that formula we just had, this is going to be the integral from 0 to 3 of the absolute value of the square root of x minus 3 halves and then plus x over 2. Okay. Then mathematically, this looks a little bit more complicated, right? Because now we need to, when we integrate an absolute value function, we need to know, namely like the transition point, right? We need to break this up using a piecewise function so that we can see exactly where that corner is going to be. Okay. So it's no different here. We need to kind of investigate just this part here. Okay. So namely, we're looking for what x value is making the inside of this positive and what x value is making the inside of it negative. Okay. And we can just solve that as we would, right, by setting this whole thing equal to 0. So it could get complicated. Here, actually, I'm gonna go down a little bit so we have a little more room, because here we'll actually want to use a substitution. Right, plus x over 2 equals 0. So first, just go ahead and multiply by 2 to get rid of the fractions. Okay, so here we're going to want to make a substitution of u equal to root x. So then u squared is equal to x. So then we have a quadratic to work with. So this is going to be u squared plus 2u minus 3 equals 0. Right, so now this is something that's factorable. So namely, this is going to be u plus 3, u minus 1 equals 0, which means u equals negative 3 or u equals 1. And because u is equal to root x, this means root x is equal to negative 3, or root x is equal to 1. Okay. Now the left one is impossible, right? The range of the square root of x is 0 to infinity, so it can't be a negative number. So we just focus on this one, which implies that x equals 1 as well, if you just square both sides. So x equals 1 is the transition point. Okay, and then you can look at, like, it's a little bit tricky here because you can't go past 0 with the square root, but you could look at, like, if you plug in like 1/2 or something for this, you should get a negative number. Maybe even 1/4 would be easier because you could take the square root of that. Ultimately, though, what that means is that, okay, this is going to be equal to the square root of x minus 3 halves plus x over 2 if x is greater than or equal to 1. And then it's going to be negative that okay, if x is less than 1. Okay. So in other words, it's just telling us that the 3 halves minus what was the original? 3 halves minus x over 2 is the larger function when x is less than 1, and square root of x is a larger function when x is greater than 1. Okay. So for the integral then, this is telling us that we integrate from 0 to 1 for this function, and then from 1 to 3 for this function. Okay. So I'll go ahead and copy everything down here. Okay, so this is what we should end up with. For the negative part, I just pulled it on the outside of the integral here, just to make it a little bit easier. Okay. So then we just go ahead and do the integral. Okay, so it's not going to be a particularly nice one, but that's okay. right? So 2/3 x to the 3/2 minus 3/2 x plus x squared over 4. And that's going from x equals 0 to x equals 1. And then we're adding it to the same thing because this is the same integral. Okay. And then we're taking this part from x equals 1 to x equals 3. Okay. So we'll go ahead and evaluate all this. So we get negative 2/3 minus 3/2 plus 1/4, and then minus a 0. And then, yeah, this one's going to be really ugly. So I won't bother trying to simplify this if it even can be simplified, really. Namely because you have the root 3 in here. So I don't think that you can really make this much nicer anyway. So I'll just go ahead and write out the exact answer here. Plus 1/4. Okay. So we'll be left with something like that. So it's going to have some kind of infinite decimal in there. So we'll just leave it at that. But the point is, I guess, that I wanted to kind of make here was, we can do it with the absolute value, and that is mathematically what we're doing. But I do think it's maybe a little bit easier and quicker to just kind of look at the graph if we can. Okay. Now we can't always do that, of course. We might not have a graphing utility, but that makes it a little bit easier just to visually see which is the larger function rather than having to test it manually. And it'll help you to find that transition point. Now, if the transition point is like a weird number, it might not even help to see the graph. So then we might have to look algebraically anyway, right? So again, to find that transition point, we're looking for where that part is 0. Okay. Okay. But yeah, so ultimately, then the general formula for the area between functions is the absolute value f of x minus g of x, the integral of that. And then the simplified version of it, when one function is strictly greater than the other, is just f of x minus g of x with no absolute value.